Okay, everyone, we are back, and we're going to look at some structural claims. So our first presenter is Adam Lohonyai, and he is the structural forensics practice lead here at Origin and Cause. He's also a designated consulting forensic engineer. He has over 10 years of industry experience and has conducted over 700 investigations. His specialties include structural failure analysis, code reviews, condition assessment of existing facilities, farm buildings, and silo failures. We also have Nabi Guderzi, who is a forensic structural engineer with over 10 years of professional practice. He's a professional engineer in Ontario, Alberta, and Atlantic Canada. He investigates and provides repair schemes for damaged and underdesigned structures and conducts structural investigations on industrial and commercial buildings. And finally, we have Simon Wynn, who is also a forensic structural engineer, and he has over 7 years of industry experience. He's a professional engineer in Alberta, British Columbia, Saskatchewan, Manitoba, California, and Illinois. And his specialties include condition assessment of existing structures, repair design of existing structures, origin and cause investigation of structural failures, code reviews, and structural damage assessments due to vibration. So I'm going to send things over to Adam, and he's gonna get things started. Yeah, let's just make sure we have the right screen. Perfect. You are muted though.
Thank you, Mark.
There we go.
And welcome everyone. So the case study that I mean, I've had many interesting cases in the past, but the one I just thought that would present today is one of an exploding silo. What's going on? Hasn't advanced the slide.
There's the there we go.
There we go. Okay. So this silo was a steel plate, like a steel silo, approximately 8 years old. It was being used to store bulk cement powder. So what I mean by cement powder is when you make concrete, you mix stones with cement and water, and the cement is the powder that mixes with water and is the binder of all the stones to create concrete. So this is just the cement powder. The silo burst open while it was being filled. So the truck operator, he stopped pumping when the pressure dropped in the tanker, which is which is a normal the normal procedure. And then he asked the silo owner whether the silo was full, and the owner insisted that the silo couldn't be full yet, based on how much how much powder the operator had delivered to the silo. So the operator then resumed pumping, and then the silo burst open shortly after the operator resumed pumping. Now, cement powder is not just some harmless dust. So it was released into the air and settled over not only the insured property, but also a little bit escaping onto neighboring properties. And the cement is caustic. So I mean, you're told to wear gloves when you're handling cement, because it can bleach your skin or cause chemical burns. Of course, it hardens when it reacts with water. So if it escapes into, say, the stormwater sewers, it can cause partial or full obstruction. So it's not just some harmless dust you can just brush off your car. There is certainly potential for property and environmental damage. So here are a couple of pictures of the silo in question. On the left, you can see, so this is the silo. It's on a raised platform so that a truck that is receiving a load of cement can back up under it, and then they can distribute the cement into it. The truck that would fill the silo would also kind of back up pretty close here. This pipe we see on the side, on the left side, is the feed pipe. So the cement is pushed through pneumatically into the silo, and then this pipe on the right is the vent pipe. And so this, so as you feed the cement powder in, you're blowing it in with air. So in order to prevent the silo from being overpressurized, the air has to escape, and so the air comes out this vent pipe. And on the right here is a close-up of where the lid ruptured. So on the left, you can see this sheet of plastic. So they covered the rupture with this plastic to prevent water from getting into the into the silo because they're still, obviously, it was still full of powder, and they didn't want to have to deal with a solid mass. They would ideally would still be able to remove the powder afterward. So this, you can see that the lid has separated at the weld to the wall. So a little bit of background about cement powder distribution, I guess. So cement powder is typically transported by these road tankers. They look similar to liquid containers. They're conveyed into the silos pneumatically. That is, the powder gets fluidized by mixing it with air, and then it's driven with air pressure into the silo. There are air vents. There are air vents at the top of the silo with filters that are intended to allow the air to leave the silo as it deposits the cement, and the filter prevents the cement powder from escaping through the air vent. The silos are not designed as pressure vessels. The road tanker is, but the silo is not. So the silo has a very low tolerance for overpressurization. Now, millions of powder of cement are handled in this manner every year. It is pretty common. This is the standard practice. Now, if the air, as I was mentioning, if the air entering the silo is not vented adequately, then delivering the powder pneumatically can overpressurize the silo, and so you can get a rupture, either the wall rupturing, or you can actually eject the filter through the vent pipe, or it can blow the silo lid off. And in this case, that's where the failure occurs, at the silo lid. So this adequate venting is critical. And this is a diagram that helps illustrate a little better. So we have the tanker. This is designed as a pressure vessel. They connect a flexible hose to the feed pipe, and then it's the cement powder is driven pneumatically into the silo. Here we have a filter. It's a little different depicted here than on what the subject silo was. Here they're also showing a pressure relief device, which is fairly common for these silos. They would have a pressure relief device in order to prevent overpressurization in case of operator error or something. So down here you'd have a pressure operating around 29 psi, but up into the silo, your pressure would be typically around 1 psi. And if you exceed that, you're putting the silo at risk of failure. So in this particular case, they didn't check they didn't actually check the level before filling. So when the operator arrives to deliver powder, the standard practice is the operator checks with the owner to verify that the level of the what the level of the powder is in the silo, so they know how much to deliver. Now, at this particular property, the owner didn't have any sensor system or anything, so the only way to check the level of the silo would be to climb up the ladder and look at it physically from the inspection board. And so they didn't bother doing this because that's too much work. So the way they checked the level was they used their handwritten records and did arithmetic to check the level. So they had handwritten records of all the powder being delivered and to the silo and how much they've discharged from the silo, and they just did the arithmetic to and estimated the volume. Cement powder is sold by mass, but obviously it's the volume that's important in the silo. So they estimated the volume based on density. The density actually varies by plus or minus 5%, depending on how long the powder has been sitting, because it settles over time. So this was not really a good way of checking the level. They also didn't have any safety features. So they didn't have a standard practice for these things is that you would have both a pressure relief valve and a warning sensors. And the warning sensors, usually you have both a high level warning sensor and a high pressure warning sensor. So if you have either detect a high level or a high pressure, you get an alarm and the operator stops pumping cement into the silo. And failing that, if it does overpressurize to some threshold, a pressure relief valve would typically be present so that the relief valve opens, and then it releases the pressure so that you don't destroy the silo. In this case, none of those were present. So it was what made this interesting for me was that everything was rudimentary. Like this was to see no safety features whatsoever in Canada in recent years. Their operation seemed almost like straight out of like Victorian England or Soviet Russia or something, where there's just complete lack of safety protocols. And with that, I'll hand things off to my colleague Nabi.
Thank you, Adam. Okay, so let me see. Okay, so do you hear me clearly?
Yes, and yeah, screen is correct.
Okay, thank you, everyone. So in this presentation, I'm going to showcase a construction project that was just recently constructed. And because of a major oversight or negligence, the recently poured concrete was cracked. So this was about reconstruction of a detached garage that was almost finished in March 2023. And the concrete slab on grade was cast in March 2023. And after that, shortly afterwards, it was settled and cracked. And also all the frost walls cracked at the corners. So this is the general view of the reconstructed garage. And this is the view of the slab on grade. You can see that there's a wide crack across the garage, and the entire slab, it has collapsed in the middle. So as a background, this was a 25 feet by 25 feet wood-framed garage with gable roof that was burnt in fire. The structural engineer at the time decided that it needs to be rebuilt, including the foundation. The frost walls and the foundation were cast in February 2023. The general contractor asked the subcontractor to place the backfill using the on-site material after the concrete were cast. And the subcontractor warned the general contractor about the frost content of the on-site material and absolved his responsibility. So the subcontractor sent a letter to the general contractor saying that because of the water content of the on-site material, we should not do that. And if you sign this letter or if you assume the responsibility, we will go ahead and do what you're asking us to do. So the GC retained a geotechnical engineer to assess the on-site material. And the geotechnical engineer approved the on-site material as a proper backfill. And the GC, after the approval of the geotechnical engineer, the GC asked the subcontractor to proceed with backfilling. The backfill was put in place in March 2023, and the concrete slab on grade was also cast in March 2023. And shortly afterwards, cracking was observed in the slab on grade and also at the corners of the frost wall. So this is a rough sketch of the section of the foundation wall and the grade. So you can see the native soil, and here is the soil that were dug up to pour the concrete foundation walls, the concrete footing. After these were poured in February, then the on-site material by that time had been sitting here like for some time, and the general contractor asked the subcontractor to use the same material for the backfill. So the whole argument is about that backfill. These are the view of the cracks at the corners of the frost walls. You can see here that the frost wall is as if it's coming out or bulging outward. Another crack, a diagonal crack at the corner of the opening at the front of the garage. You can see here wide cracks at the bottom of the opening of the garage. Another view of the crack in the slab. You can see here that the slab has obviously collapsed by about 4 or 5 inches. Now, so let's see what happened that resulted in this failure. So first of all, the frost walls were cast in February 2023. This is casting concrete in the heart of winter, like Canadian winter. So this ideally should be avoided, and if it is absolutely has to be done, special measures needs to be taken. Like you need to heat up the material beforehand, and also make sure that during the concrete casting and afterwards, the material temperature remains above 5 degrees, and at least for 48 hours to make sure that the concrete does not freeze. The general contractor, okay, here actually not only that, so when you pour the concrete, also you need to protect the soil around the concrete footing against frost. Now, the general contractor asked the subcontractor to place backfill using on-site material. So the on-site material was sitting there for months, and they were full of water and frost. And the general contractor was warned about it by the subcontractor. So subcontractor warned the GC about the frost content, and the subcontractor also did his due diligence by saying that if you push us to go ahead, we are not responsible for any failure. So GC retained a geotechnical engineer to assess the on-site material, which was a good approach. However, the scope of retention of the geotechnical engineer was very limited. So the geotechnical engineer provided a memo, and it was just saying that the on-site material was proper for the backfilling. Now, in the same memo, it said that the on-site material is fully saturated, it's brown silty soil and fully saturated, but it had no comment on timing and procedure of backfilling, like when to put the backfill, and how to dry the material if it should be dried, or how to drain it off. And no comment on drainage. So it was just a one-page memo. So the scope of retention of the engineer was not inclusive enough. So geotechnical engineer approved the on-site material as backfill, very limited recommendations, and also it had no stamp. Any engineering report or drawing that is to be relied upon has to be sealed with the stamp of the engineer. If it's not sealed, it means that it's just a draft. Now, if it's really a draft, the engineer should tell the client that this is just a draft. This is not to be relied upon. We are still working on it to do the final report. But if it's not a draft, and if it's final, it has to be sealed. So GC asked the SC to proceed with the backfilling, of course, after approval of the after the memo of the geotechnical engineer. And the backfill was put in place in March 2023. And the backfill, of course, backfilling was with the on-site material, was full of water and frost. The concrete slab on grade was cast in March 2023. Shortly afterwards, cracking was observed in the slab on grade and frost walls. And the cause of the cracks and collapse of the slab on grade was subsidence of soil, the saturated soil after the backfilling. So as a conclusion, just to summarize what factors resulted in this failure and how it could have been prevented. First of all, the scope of geotechnical engineering services should include recommendations on backfilling, drainage, type of soil. So a typical geotechnical engineer is very inclusive. This was not the case on this file. And special measures must be taken for pouring concrete during winter and should ideally be avoided. And if it has to be done, the structural engineer should give recommendations on how to pour concrete, what guidelines to follow, how to heat it up, how to protect the concrete from freezing, and how to protect the soil from frost. And plus, ideally, it should be avoided. And generally, in any report, any final report that is prepared by an engineer and that is to be relied upon must be sealed with the engineer's stamp. And if something is not final, the client should be advised about it, and it should not be implemented. Thank you very much. And with that, I pass it off to my colleague, Simon.
All right, thank you, Navi. Do you guys see my correct screen?
Yes, you just have, yeah,
Yes.
there we go. Perfect.
Is it this screen, right, with the mouse on it? I hope.
Yeah, looks
Okay,
good.
okay. All right, thanks, Navi, thanks, Mark, and hello, everyone. I'm going to talk about the interesting claim that we worked on in the past. Um, in this claim, a building located in Caston, Alberta, suffered severe damage and a partial collapse after a windstorm in November 2021. Before the collapse, the building was still under construction, and our task on this claim was to investigate the root cause of the collapse. Did the building collapse due to the windstorm or due to some other reason? So this slide shows the building's condition immediately before the date of loss. The building had a footprint of approximately 60 feet by 80 feet, with the exterior wall standing as rough around 16 feet in height. The highest point of the building, which is roof pitch right here, reached roughly 27 feet. So the building was not very big, but still it was pretty significant in size. As you can see, the construction was only partially finished, and one side of the building was completely open. Such partial completed buildings like this is typically unstable by itself and requires temporary bracing, like these, to withstand various expected loads, including construction load, wind, snow, and seismic loads. We'll delve into the topic of temporary bracings or force work later in the presentation. In the slides, you can see the building's condition on the morning following the windstorm. Half of the building has collapsed, and the remaining roof portion right here appear somewhat distorted. So was this damage solely due to wind? We will explore this question in more details. Before that, let me provide some context for this claim. Our involvement actually didn't begin until after the building has been demolished and reconstructed. We was retained by the adjuster representing the insurer of the framing contractors, who was the insurer in this case. Prior to our involvement, there's a couple of other experts that had already involved, and they already investigate the cause of the collapse, but they have different and conflicting opinions. The expert representing the building owner claimed that the collapse occurred due to the buildings being left unprotected against the wind during construction by the insurer, the framing contractors. On the other hand, the expert representing the insurer view that the windstorm was the cause and that the insurer had provided some protection during construction. So who was right in this case? That's why we came in. Origin and cause were tasked to conduct an independent investigation and offer a second opinion on the cause of loss. We was provided with photographs taken by the insurers before and after the windstorm, as well as some construction documents related to the collapsed building. So our initial step in the investigation was to determine whether wind was the primary cause of the collapse or not. To do this, we gather wind data for the date of loss from 3 nearby weather stations. We then compare the maximum wind gust speed recorded at these stations with the minimum requirements outlined in the applicable building code. Based on the data collected from the weather station, we found that the maximum wind gust speed at the site of the incident were approximately 100 to 120 km per hour on the date of loss. Looking at the building code, climatic load specification, this building and any of its force work was required to be designed for the minimum wind gust speed of around 150 km per hour. This is greater than the wind speed that we collected at the weather station. which is about 100 and 120 kilometers per hour maximum. Given this information, if the building structures and the false work met the building code requirements, it is very unlikely that the subject building would collapse. So we can conclude that wind was not the root cause of the collapse. It was something else. So the previous expert representing the insurer was wrong. After ruling out wind, our next step involved a thorough review of the photographs supplied by the contractors and analysis of the construction document pertaining to the building. Upon completing our review, we made several important discoveries. First, the roof trusses were connected to the exterior walls with only 3 toe nails at each end. This was surprising, considering the truss had a span about 60 feet. We'll delve deeper into this finding in the upcoming slide. The second, there was some diagonal braces attached to the exterior walls as an effort to provide bracings for these walls during construction. So the building was not completely unprotected during construction, like the first expert representing the building owner claimed. However, the question that arises is whether these braces were sufficient to protect the building against all the expected loads, which we'll address in the subsequent slide. And lastly, during our investigation, we couldn't identify the engineer of record for the building. After some conversation with the insurer, we discovered that there was no engineer of record, which was surprising for the building of this size. Now, let's delve deeper into each of the findings. So number one, roof trusses to wall connection. In the left photo, you can see the connection between the roof trusses and the top plate of the exterior wall. There was really nothing here. Through a discussion with the insurer and a review of the provided photographs, we found that the trusses were toe-nailed to the wall double top plate with only 3.25 inches nails at each end. This practice is standard for small buildings that don't require engineering. However, in accordance with the National Building Code, this standard practice doesn't apply to buildings with roof trusses exceeding 40 feet in span. In our case, the roof trusses had a span of 60 feet. Typically, for buildings that have long roof span like this, trusses need to be secured to the wall double top plate using hurricane ties, because toenails lack the capacity to withstand the wind uplift forces that the truss likely experience. The photo on the right displays example of these hurricane ties. These ties have much higher uplift capacity than the toenail connection. And we did some calculation to verify the capacity. Our calculation indicated that the toenail connection could safely resist a maximum wind speed of approximately 50 kilometers per hour, while the maximum wind gust speed at the subject site on the day of loss were approximately 100 to 120 kilometers per hour. Thus, this connection was severely undersized, which led to the roof trusses being detached from the walls and lifted up during the windstorm. And this was the primary cause of the building collapse. Second finding, temporary false work. From the photos provided to us, it was evident that the temporary false work installed by the insurer to brace the exterior walls against wind load was inadequate. This false work feature, LVL braces, which was anchored to concrete block at one end and attached to the wall stud at the other end using wood screw. The first photograph taken before the storm showed that the braces had been installed. The second photograph captured after the storm, so one of the braces has failed right here. It's collapsed. In the third photograph, also taken after the storm, most of the braces remained standing, but one was significantly bent. This one right here, the far end, it bent a little out of plane. So we did ask the insurer, why they use toenails instead of well, before that, we did wondering, why these fail, and And then after we did some study, we found that it was too slender for the task. To properly support the structure, either there should have been more braces or they should have used larger member for the braces. Such mistake could have been easily prevented as the insurer retained an engineer to design their force work. So we discussed with the insurer to understand why they used toenails instead of hurricane ties and why they did not involve an engineer to have them to design their force work. The insurer explained that the toenails connection was their standard practice and there was no detail in the construction drawings showing the required hurricane ties. They also were not aware that the force work for the subject building needed to be engineered, and it was not clear from the construction document that the building needed to be engineered. To get a deeper understanding, we conducted a thorough review of all available construction documents related to the subject building, leading to our third significant finding. We discovered that the building was not engineered, which might be okay. This was a small building and met certain requirements of the building code, but definitely not for this building with a long roof span of 60 feet. The general contractor did not engage an engineer to aid in the design of the building, even though the building was required to be engineered based on its roof span per the National Building Code. As a result, the construction document provided to our insurer was poorly put together, lacked many important details, including how to properly fasten the trusses to the walls, and generally fell below the minimum accepted standard expected from a competent professional engineer. And that could be the reason why the framing contractors, who is our insurer, did not do a proper job, because it was building based off a terrible set of construction documents provided by the general contractor. So in summary, although the subject building likely experienced heavy wind gusts on the day of loss, it was not the primary cause of the collapse. The incident was primarily due to the failure of the toenail truss to wall plate connection and the temporary force work, which was installed by the framing contractors, our insurer. These connections and temporary structures was not engineered and did not meet the requirement of the applicable building code for the subject building and location. However, framing contractor should not be the only one to be blamed for this collapse. There was other major contributing factor as well. The building was not designed by an engineer, despite this being the requirement of the applicable building code, which resulted in a substandard set of construction document with numerous important details and information missing. And this is a general contractor fault, and they should be held liable as well. Additionally, it is worth noting that the company responsible for reviewing and approving the building permit failed to fulfill their duties, allowing the construction of the building despite clearly not meeting the applicable building code requirement. In cases like this, it is common for people to jump to conclusion that natural disaster, windstorm, is obvious and most likely cause of loss. However, as I have just presented, the devil is in the details. So that is the end of my presentation. Let's move on to Q&A.
All right, thank you, Simon. Thank you, Adam. Thank you, Navi. Yeah, if anybody has questions, and I see some coming in now, yeah, please feel free to submit them. So is everybody, Adam, are you there? Navi, still there?
I'm here.
All right, so we've got one for you, Adam. So is it possible that the powder settled in the horizontal section of the vent pipe and hardened from atmospheric humidity blocking the vent? Why did the solo fail this time and not in the past?
So that certainly didn't happen in this case. I didn't share all the details, but so the way this guy filter, it was very rudimentary. So he didn't have a filter sock on the vent pipe as what you would typically see. Instead, he had the vent pipe terminate in a barrel of water, and so any air would bubble up through the water, and the water would capture the cement dust. And in this case, like the incident, there was there was a huge amount of cement blown through the air vent pipe and into the barrel. So like after the incident, when I attended the site, the barrel was like a third full of hardened cement. Now the other reason we can conclude that that's not what happened in this case is because based on the arithmetic of the owner's recorded comings and goings from the silo, there should have been about 40,000, roughly 40,000 pounds of cement powder at the time that the overpressurization occurred. And they in fact removed about 60,000 pounds. So somewhere along the way, their method, because they didn't have checks and balances or safety features involved, somewhere along the way, they've introduced either one blunder, or an accumulation of small errors that resulted in the amount that they estimated being the amount that there's a discrepancy of about 20,000 pounds between how much powder was they thought was in the silo versus what was actually in the silo.
Okay, fantastic. I think it covers that. Simon, I've got a couple questions for you here. So first one, would the building inspector not pick up on these issues? And I think you touched on that briefly in your case study.
So we were not aware that there was any building inspector in the first place. The building, so this is in Caston, Alberta. They did not a dedicated department for plan reviewing or building inspection. So they sub out their work to a third-party company, and based on their review of their work, they just approved the building, the construction of the building, even though it didn't meet the building code requirements. So I'm not sure if there was any building inspector that was there. And also, I think the building inspector would not be involved until the building was finished with the framing, and right before the windstorm, they haven't finished the wood framing yet. It's still partially open. So I'm not sure if there was a building inspector involved at the time of loss.
Okay, so here's a second question for you, and this is something that we touched on when we ran through this the other day. It seems that many farm buildings are not typically engineered. Is there a requirement in Alberta that farm buildings with a span of more than 40 feet be engineered?
Yes, even though it's a farm building, but if the roof or floor span of the building exceed 40 feet, it will need to be engineered. This is based on the National Building Code and also the Alberta Building Code as well.
I just want to clarify. So Alberta exempts farm buildings, but this would not have qualified as a farm building.
Okay, thank you for the clarification. Navi, one for you.
Yeah.
Why did the garage concrete have to be poured in the winter?
So the general contractor wanted to expedite the process and finish the work. That's that's from my understanding from the conversations I had. Yeah.
So is there anything they could have done, short of not pouring in the winter, to avoid the cracking of the foundation? A different backfill material, would that have?
So first of all, like, let's say if it had to be built during the winter, like, they should have first of all contacted the structural engineer on record and asked for instructions, and also the scope of the geotechnical engineer should have included what to place as the backfill, like how to place the backfill, how to drain the site, and also the other thing is the structural engineer specified on the drawings that the strength of the soil, the bearing capacity of the soil should be verified by a geotechnical engineer. this was not done on this site either. So yeah, so the engineers must have been involved if it had to be built during winter time.
Okay. Adam, is it hard to change the filter? And you have to go right into the silo to change it?
Yeah, I don't know the specifics of how the particular filter work, and there are different systems, right? There are different options available. So I don't know how difficult it is to change a filter sock.
Okay, let's see if we have anything else. Issues. Here.